Welcome to another fabulous day of Calculus 3. We're going to be doing independence of path with vector fields, and that includes the fundamental theorem of line integrals. Wow, really powerful theorem. You're going to love this. This is really exciting stuff. Okay, but first, we're going to be doing some review of some line integrals. Yeah? Oh my, what kind of review? Well, last time we did a couple of different types of line integrals, the type 2 and type 3. Type 2 is FDR, and type 3 is differential form. So let's do some more of that, as well as parameterizing and things like that. So it's kind of a good kind of catch up with these next two pages. And there's going to be sort of a lesson to be learned from these two pages that we're doing as we do some review of line integrals. So keep your eye open for what that would be. What is the moral of the story? Okay, first up, we're going to do this line integral right here in example 1, and we're going to do it 3 separate times. What? Yeah, we're going to do that line integral 3 different times for 3 different curves. Wow, what is the point of all this? This seems like a lot of work. Well, it is going to be kind of cool because we're doing this line integral 3 different times for 3 different curves, and the curves do share one thing in common. All 3 of the different curves will share the beginning point, the start point, and the ending point in common. So that's something to take a look at. Okay, so letter A, the curve C consists of the line segment from the point 2, 1. Okay, let's locate that. Over here to the point, you got to do an arrow here for orientation, to the point 4, 1. And then from the point 4, 1 up to the point 4, 5. Okay, so there's like another leg of the journey here. It's going to go from here to here like that and stop at the point 4, 5. Okay, so this particular curve is what we call piecewise smooth because it does have a sharp corner in it right there. It kind of goes whoop and then, to the right and then straight up. But that's okay. We can do line integrals on piecewise smooth curves. And the way we do that is we have to do 2 separate line integrals. So what am I saying? That this curve C is the union of C1 and C2, where C1 is the straight line going to the right, and then C2 is the straight line going vertically upward. So we're going to have to parameterize twice, and we're going to have to do 2 separate line integrals. So here we go. What we're saying is that this line integral, xy dx plus x squared dy, this is part A here, will have to be broken up into 2 separate line integrals. We'll do a C1 xy dx plus x squared dy plus a second line integral for the other leg of the journey. And then we'll add the results to get our final answer. So we'll do this piecewise for the piecewise smooth curve. Okay, so first up, this. So we need to parameterize C1, which is really easy because it's just a straight line. So C1 will use the vector valued function R1 of t, and it's a 2D curve, so it's 2D vector valued function. And on this, right here, on this curve, we start at the point 2, 1, and we finish at the point 4, 1. So that's kind of easy because it looks like the y coordinate stays the same the whole time. So the y coordinate is a 1 the whole way, and it looks like the x coordinate is changing. So we'll let him be t. And in order to match the curve, since it starts at the point 2, 1 and finishes at the point 4, 1, how about if we have our time start at 2 seconds and finish at 4 seconds? That'll work. Yeah. So then we're going to get R1 prime. And why do we need R1 prime? Because when you're doing one of these line integrals, you need the velocity vector. The dx will get replaced with a 1. from the R1 prime. And the dy will get replaced with a y component of R1 prime, which is 0. That's going to make this real easy. Okay, so what is this line integral xy dx plus x squared dy become? It becomes a regular integral going from time 2 to 4 seconds. Well, how come 2 to 4 seconds? Because we deemed that the case when we parameterized the curve. And then the x and y's get replaced with the x component and y component that we cherry pick from the vector valued function. So x times y becomes t times 1. And then dx, as we stated, was 1. Technically, it's 1 dt plus x squared, which is t squared dy. But remember, the dy was 0. Oh, that's nice. So that guy goes away. Fine. So what do we really have to worry about? We just have to worry about integrating t dt. That's easy. It's t squared over 2. And we'll evaluate between the limits 2 and 4. And when we do this, we get a number. And what do we get? I think we get 6. Okay, save that for later. Well, what do you mean? We're not done. We're still doing part A. Really? Yeah. So now what? Well, the second leg of the journey is C2 here. So we need to parameterize C2. And that's going to be pretty easy because it's a straight line. And we'll call the vector valued function R2 of t. And it looks like on that vertical line, the x coordinate stays constant the whole time. It's a 4 the whole entire time. But y is the one that's variable. So how about we let that variable be t? And since y starts at 1 and finishes at 5, how about we let time go from 1 second to 5 seconds? That'll work. And then we go ahead and get R2 prime, which is easy. It's just 0, 1. And remember, this is going to be the dx, and this y component will be the dy. So then this line integral xy dx plus x squared dy becomes the line integral from 1 to 5. And then x times y will be 4 times t. And then dx is 0. Oh, that's nice because that term goes away. Plus x squared dy. So we have the x component 4 squared. Dy is 1 dt. Oh, so this is pretty easy because we're just integrating 16 with respect to time. Easy peasy. That's just 16t going between 1 and 5. Well, I'll let you do the arithmetic. I get 64. So the final answer is 6 plus 64, which is 70. So we're done with letter A. Great. But we've got 2 more to go. We have letter B and letter C. Let's go ahead and do that. Now, letter B, the line integral is going to be evaluated on a straight line segment that begins at the point 2, 1. Okay, so it has the same starting point as that other line integral. And it finishes at 4, 5. So it's a straight shot. Okay, now there's 2 ways to parameterize this. You guys can use your algebra where 2 points determine a line, and you can go get the slope where you do the change of y over the change of x. And then you go use the point slope form and so on. That's one way to do it. Another way to do it is use your knowledge of parameterizing lines that you learned in 3D, but we'll apply it to 2D. What is the what's the direction vector? So the direction vector is terminal minus initial, and we'll just call it V. And so if you're going to do that, you're going to go, okay, 4 minus 2, and then the y differences are 5 minus 1. So this is 2, 4. And then if you do the parametric equation, z is equal to 0 because we're in the xy plane. You pick one of the points. How about if I pick the point 2, 1? And then you could go, okay, I could do it like this, 2 plus 2t. and then 1 plus 4t. And then what is time going to vary from? Remember, you need to match the curves starting and stopping points. You need to start at 2, 1 and finish at 4, 5. Well, for this parameterization, I claim that if I let t start at 0, that will, and I plug it into this. By the way, the vector valued function, we'll just call it r of t, is going to have 2 plus 2t and 1 plus 4t as the components. And then what value of time will finish at the correct location? Like, what do I have to have time be in order to have the ending point be 4, 5? What do you guys think? Any ideas?
1.
Good. 1 will work, because if you substitute that into 2 plus 2t and 1 plus 4t, you'll get the 4, 5. So here's our parameterization. And now we can go get r prime, because we're going to need that. And that looks like it's a constant vector. Yay. And then, so we're still doing letter B here. So we're going to do this line integral, xy dx plus x squared dy. It becomes this regular integral going between time 0 to 1 second. And then x times y, that's going to be 2 plus 2t times 1 plus 4t times, and this right here is your dx, 2 dt, plus, and then x squared dy becomes 2 plus 2t squared times dy here, 4 dt. And this is going to be a little bit of a hot mess, because you're going to want to FOIL and maybe even FOIL that out. I'm just going to put et cetera, go find the antiderivative and go ahead and evaluate at the limits. You should get 170 thirds. Okay, we're done with part B. So what's letter C? Gotta do this all over again. The letter C is nicer, because in letter C, they were very kind, because they gave us the parameterization. Oh, nice. And if you go to your graphing calculator, you can see what the graph would look like. It's not going to be a straight line, that's for sure. It appears like it's going to be the portion of a parabola. Oh, I don't know if this is coming up or not. It takes a while. Okay, here we go. There it is. Okay, so I'm going to go into my mode, and I'm in parametric mode. That's good. So I'll get out of that, and then I'll clear this out. And let's see what this graph looks like. So this is going to have the x component be 3t minus 1. And then the y component will be 3t squared, minus 2t. And in the window, we'll set our t minimum. They want us to have the t minimum be 1 second. And the t max is 5/3 seconds. And let's graph it. Whoa! Kind of looks like it's a straight line, but it really is not a straight line. If you zoom in a little bit, it's actually a portion of a parabola. Oh, it still doesn't look good. Yeah, never mind. Of course, it's not cooperating. So it turns out it's got a little bit of a curve to it. It has the same starting and stopping points as the other curves, but it's a portion of a parabola. So it's got a little bit of a curve to it. Okay, but it still begins at 2, 1 and ends at 4, 5. So if we're going to do this line integral, since they gave us the vector valued function, the R1, or the R prime rather, is simply going to be what, 3 and then 6t minus 2. So remember, this is the dx, and this whole thing right here is the dy. So this line integral, xy dx plus x squared dy, becomes the regular integral going from 1 to 5/3, x times y. The x component was 3t minus 1, multiply that by 3t squared minus 2t times the dx, 3 dt, and I got to go drop to the next line, I'm running out of room, plus x squared dy, 3t minus 1 squared times the 6t minus 2 dt. Okay, So this is also going to be a little bit of an algebraic nightmare. I don't feel like doing a whole bunch of algebra before I integrate. Whip out your graphing calculator and use your FNINT menu item there. But you should get 58. So what is the moral of the story for this page? We had 3 different line integrals. Well, the same line integral, but 3 different paths. And the paths did have a common denominator. They all had the same starting point and same ending point, but we got 3 different answers. Yeah, so what? Doesn't really do much for us. Okay, next page. So this next example we're about to do, we're going to do a line integral 3 times over again. And again, we'll have 3 different paths. And we're going to have to parameterize a lot. This is good practice parameterizing, because you're going to get experience parameterizing on your own. And so it's good to see lots of examples. But the thing here that's going to happen is, even though the paths also have that common denominator of the same starting point and same ending point, something else is going on here. So take a look. And before we start, there's a physics fact here. Our physics brethren have. In a gravitational field, and keep in mind a gravitational field is a vector field. Yes, indeed. The work done by gravity on an object moving between 2 points in that field is independent of path taken by the object. What does that mean? It means that if I were walking from a point to another point, it doesn't matter if I do a straight line shot between those 2 points or if I zigzag, and as long as I end up at the same destination, the work done on my body as I move between those 2 points will be the same. Well, it seems like if you do the zigzag, it should be more work because, it took you longer. Well, we're talking about not work done by me, calories wise or anything. We're talking about the work done by the vector field on me. That's a different kind of conversation. Turn out it's going to be the same work. And that's key, because the generalization of that result is going to take us to the fundamental theorem of line integrals, which is the meat and potatoes of this section. Okay, so here we go. Example 2. This one has a little bit different flavor because instead of a differential form line integral like the previous page, the line integrals we're going to be working on here are the FDR type, the dot product between the vector field and the velocity vector. So here's our vector field given to us. It looks like there's a typo there. Get rid of that M. And we're going to be going from the point 0, 0 to the point 1, 1, 3 different ways. Oh, yeah. So the first way is going to be a straight shot. So the first curve is just going to go boom, straight line. The second curve, the C2, is going to be x equals y squared, which is a portion of the sideways parabola. So it's going to be going like this. That's C2. And then the last line integral we're going to be doing will, same starting and stopping point, but it's going to go along a cubic path, which kind of looks like this. That's C3. And they didn't give us the parameterization for any of these curves. So we're going to have to do the heavy lifting there. No worries, we can do it. It's not that hard because all 3 of these are functions of x. So that makes it really easy to parameterize. Okay, so for letter A, I'm going to call my vector valued function R1 of t. And since I'm just going along y equals x, let x be t. And then since y equals x, y is equal to t also. And then time will go from 0 to 1 second, and that will match the starting point of 0, 0 and the ending point of 1, 1. We're going to go ahead and get R1 prime because we're going to need it. And then work is the line integral f dot dr. So that line integral is going to become a regular integral going from 0 to 1, and we're going to take the dot product between the vector valued function and the velocity vector, and then we'll integrate with respect to time t. Now, the vector valued function has components a half xy, but a quarter x squared for the y. But you don't want to have x's and y's in your line integral. Oh, well, then what do we put instead? Well, you're going to substitute in place of x, anytime you see an x, the x component of your vector valued function, which is t. And for y, you'll substitute the y component, which also happens to be t for this guy. Okay, so then 1/2 xy is going to become 1/2 t times t, which is t squared. And then 1/4 x squared will become 1/4 t squared. That was easy. And now we're ready to take the dot product. And you guys know how to do dot products. You're going to take this guy times this guy, so 1/2 t squared times 1 plus 1/4 t squared times 1. And these are both like terms. So let's just go ahead and add them before integrating. You don't have to, but it makes it easier. I get 1/2 is 3/4, right? And 1/2 plus 1/4 is 3/4. So we get 3/4 t squared. I think that'll work. And this is pretty easy to integrate. I get 1/4 what? T cubed, going between 0 and 1. So final answer, I get 1/4. Okay, I'm done with letter A. That was pretty easy. So the work done is 1/4. So let's do letter B. We have to parameterize. Now this letter B is a function of y, not a function of x. Well, how do you know? Because the way they gave it to us, the x equals something. That's the format for a function of y. So if you're parameterizing a function of y, you want to let y equal t instead of the x. And then since x is equal to y squared, x will be t squared. And once again, we have to figure out what the range is for time t. But if we let t go from 0 to 1, it will match the curve. Okay? We go ahead and get our 2 prime. So I get 2t and 1. Okay, so then the work done is the line integral f dot dr, which for us will be the regular integral going from 0 to 1. We're going to have to take a dot product again. Okay, don't forget to put your velocity vector in there. And then you have to rewrite your force field in terms of this problem. So your components for your vector field, 1/2 xy, what will that look like? That'll look like 1/2 times the x component, which is t squared, times y, but that's t. And we'll clean that up in a minute. And then the other component of this vector field was 1/4 x squared. So that looks like it's going to be 1/4 t squared squared. So be careful because we got a lot of exponent laws here. I'm going to clean this up a little bit before I take the dot product, just to, rewrite things as single powers of t. So this looks like it's going to be 1/2 t cubed in there, and then t squared squared. That's going to be 1/4 t to the 4th. Now let's go ahead and take this dot product. Pretty easy peasy here. So I get the product of 1/2 t cubed with 2t plus the 1/4 t to the 4th multiplied by 1. And this whole thing you're going to integrate with respect to t. It turns out that you're going to get a couple of t to the 4th terms. When you multiply 1/2 t cubed times 2t, that's just going to be t to the 4th. So if you add that to 1/4 t to the 4th, that's going to give you 5/4 t to the 4th. So you're really just integrating 5/4 t to the 4th, which is pretty easy. On the page here because we're running out of room, of course. So you're going to integrate 5/4 t to the 4th. And then what does that give you? Well, let's see, 1/4 t to the 5th going from 0 to 1. And I get 1/4 again. Okay. So we're done with letter B. Letter C was the cubic, and that is a function of x. So we're going to parameterize again and do this whole problem one more time. So to parameterize y equals x cubed, we'll call it R3. And we'll let x be t, and y is equal to x cubed, so let y cubed. And time going from 0 to 1 second will work again. Go ahead and get our R3 prime. And so the is equal to this FDR line integral, which is the regular integral going from 0 to 1. You're going to take a dot product. Don't forget to use your velocity vector. And so now you have to convert your vector field into t again, a half xy, quarter x squared. Okay. Half xy, 1/2 t cubed, because I'm taking the x and y components from the vector value function. And then a quarter x squared, that looks like it'll be a quarter t squared. Okay, so this is what, 1/2 t to the 4th. Okay, so let's do the dot product next. So you're going to take a half t to the 4th and multiply it with 1 plus a quarter t squared and multiply it with 3t squared, and then finally integrate with respect to t. But it turns out both of these terms are like, which is kind of nice. That doesn't always happen, but we can combine them before integrating just to make it a little easier on ourselves. I mean, you don't have to. You'll still get the same answer. Okay. Didn't we just do this? I thought we already did this. Yeah. So 1/4 t to the 5th going from 0 to 1. And we get 1/4 again. Okay. So we got the same answer for all three of these. So the work is the same no matter what. So what do we notice about the three answers? They're the same. Now, here's the key question. Is this vector field conservative? And we talked about last week the test to determine if a vector field is conservative or not. And so remember, if I call the first component M as in Mary, and the second component N as in Nancy, you check by seeing if dm dy is the same as dn dx. So let's go do those partials right now. So the partial with respect to the partial of M with respect to y looks like it's a half x, and the partial of n with respect to x is 2/4 x, but that's a half x also. So that they are the same, and so yes, it's conservative. Answer yes. So what does that mean? You can go get the potential function. Remember, go get mama. So let's go do that now. This is review from last time. Remember, please do it my way, otherwise you will lose points. For those of you that are going to go use the view an example button and do the recovering potential function the textbook way, I will dock you points. Even if your final answer is correct, I want you to do it my way in this particular case. Okay, I'm going to be a little bit adamant about that. So we're going to recover the potential function. What does that mean? You're going to integrate M with respect to X and then N with respect to Y. And then you'll add the results while not adding the duplicates together. If there are any duplicates, just take one instance. Remember this? And there's some notation in here also that if you fail to do it on your handwritten work, I will dock you points. So we'll talk about it again, just in case you forgot from last week. So the M for this vector field, that's the first component, a half xy. You're going to integrate that with respect to x. Okay, I believe that's going to be 1/4 x squared y. And you don't put plus c, but you're going to put plus something. Since you only recovered part of the potential function you integrated with respect to x, there could be just a constant still to go. And there may be some stuff that has to do with the other variable, y. So that's why I want to see you put h of y, some function of y is going to go there. If you fail to do this, remember, I will take away points. I'm warning you now. If you want to maximize your points, do it this way. So the n for this vector field is the second component, a quarter x squared. You're going to integrate this with respect to y. And that is also going to be a quarter x squared y plus some function g of x. Now, I want you to notice here, you have duplicates. Do not add them together. Do not add them together. If you do that, prepare to die. Okay? I'm not going to give you any credit. You didn't listen. What does that mean? The potential function fxy, and I do want you to write fxy, write down who this function is equal to 1/4 x squared y plus some constant. Okay, let's save that for later. We're going to come back to that. The reason why is I want to go over the fundamental theorem of line integrals, and then we're going to apply the fundamental theorem of line integrals. But we need the potential function in order to do it. Yeah, cool. All right, are you guys ready? I don't know if you're ready. Should I tell you what the fundamental theorem of line integrals is? I don't know.
Yes, please.
I think you need to tell me what the fundamental theorem of calculus is first. Yeah? So before we talk about the fundamental theorem of line integrals, let's do a pop quiz here. What is the fundamental theorem of calculus? And you learned this in Calc 1. Does anybody know it?
Is it when you take the integral and then evaluate b minus a?
Okay, so you take an integral. Yeah. And then?
FB minus FA.
Good. I'm going to do an intermediate step. You get some antiderivative that you will evaluate between the limits. Perfect. And then f of b minus f of a. Very nice. Good job. That's part 1. What is part 2? There actually is a part 2 for the fundamental theorem. Really? Yeah, we're going to need both parts. Sorry.
Isn't when you just replace b with x?
Well, it's basically showing that the integral of a derivative is the function, that they're inverse operations. So part 2 has this kind of flavor to it. You take the integral, say from a to x, and then here you have d dt of f of t, like this. Have you guys seen this?
Yeah.
It basically is saying that if you're going to integrate a derivative, because integration and differentiation are inverse operations of each other, you'll just get the function. It's like, oh, okay. And then you'll evaluate it between whatever the limits are. And so here, f of t minus f of a. Okay, so that's basically the part 2 of the fundamental theorem of calculus. Now, let's do the fundamental theorem of line integrals. Why did you do this first? Because you're going to see it's almost the same. It's got the same flavor to it. So if you know the fundamental theorem of calculus, it's easy peasy to grasp the fundamental theorem of line integrals. Yeah. All right, now you're ready. So you got a curve, C, piecewise smooth, lying on some open region R. And let's say it's parameterized, R of t. And they tell you what the range is for your time t. And let's say you have a vector field, Mn, and it's conservative. Underline this like 3 times, because this theorem will not work if your vector field is not conservative. So don't use it all the time. Otherwise, you're going to get yourself into some trouble. and you need M and N to be continuous in the region, fine. Then what can you say? Well, we're going to fill in the blank here. If you're trying to do one of these line integrals that involve a vector field like FDR, instead of going through all the hard work and parameterizing and all that other stuff that we just did at the beginning of this lecture, you don't have to. What you're going to do is the vector field's conservative, which means that he's mama's gradient. That means that, and I'm going to even write that, I'm going to replace the vector field with the gradient of some scalar function f. So he's somebody's gradient dot dr. And that is just going to be the mama function evaluated between a starting point, we'll say t equals a seconds, to t equals b seconds. So that's going to have this look to it. F evaluated at x of b, y of b, minus f evaluated at x of a, y of a, okay? Where x of a, y of a is equal to the starting point of your curve, and x of b, y of b are simply the coordinates of the ending point of your curve, okay? And also f is a potential function. That's the mama function that I talked about, the potential function for the vector field f. Okay. So what is so cool about this fundamental theorem? What's cool about it is you can use it anytime you're trying to do a line integral and the vector field's conservative. You can totally bypass parameterizing. Like you can skip it. Really? Yeah, because parameterizing is kind of tedious. You don't have to do any parameterizing. You don't even care what the curve looks like. All you care about is, did they give you the starting point and did they give you the ending point? Because that's all you need. And then you just substitute in the starting point and the ending point to your mama function. And you do have to prove that the vector field's conservative. And yes, you have to go get mama. But then once you do, you're almost done. Okay? I'm going to prove the theorem right now, and then we will use it for a previous example. Okay, so the proof is kind of cool, and we're going to assume that the curve C is smooth. Smooth meaning no sharp corners or cusps, because then otherwise it's kind of a hassle to do the proof. And here, because we're given that F is a conservative vector field, that means we're guaranteed F has a mama. F has a potential function. It has a potential function fxy, and the vector field is automatically equivalent to the gradient of mama. It's understood, okay? So this gradient, and you guys all know about gradients from a previous module in this course, it's just a vector that contains the partials for that scalar function, that's all. Yeah, then it follows that this f dotted with dr, the FDR line integral, is going to become this regular integral that's going to look like this. The integral going from a to b. Your vector field dot product with dr dt, that's the velocity vector. And I'll rewrite it a different way. Since this vector field is the same as the gradient, it's just going to be a vector that contains the partials, and you're going to take the dot product of that with dx dt dy dt and integrate with respect to t. Okay, fine. And this is the exciting part, folks. This is the part of the proof, I'm almost done, that is like so cool. I'm so excited for you because you know why? The fact that you've made it this far in this course is why you're going to totally understand these next couple of steps. And that's so cool. Aren't you grateful you stayed for this? I mean, you'll see. Okay, so let me keep going. I'm gonna actually take the dot product. Okay, so what do you mean? I'm gonna have, you know, the fx, xy times the dx dt plus the other partial times dy dt. Okay, fine. dt. Okay, now here's the part where you guys, you know this. Doesn't this look like somebody did a chain rule? I'll even do another step. I'll replace the fx with the fdx so you can see what I'm talking about. Look at this, folks. Check this out. Doesn't that look like the chain rule? Somebody did the chain rule on something.
It looks magical. It is.
That is the chain rule, people. Somebody did a chain rule. What do you mean? I mean, you had some f up here, you know, that was a function of x and y, and x and y were both functions of t. Remember these little schematics? You guys should be so excited right now. I'm excited for you. So what am I saying? I'm going to replace that big old chain rule with what it is. It is basically d dt of the function f up here at the top of our tree. dt. Yeah. So this chain rule here is df dt. And that's basically what I'm replacing it with. Now comes the last step. I am now going to use the part 2 of the fundamental theorem of calculus to finish this proof. So remember, when you integrate a derivative, what do you get? Since integration and differentiation are inverse operations of each other. You're taking the integral here of a derivative here. You see that? So what's left? You're just going to have the fxy, where you'll evaluate it between time going between a and b seconds. And that is going to give you what I mentioned, f evaluated at x of b, y of b, minus f evaluated at x of a, y of a. And that's just going to be some number, okay? And we're done. End of proof, QED. And that is by the fundamental theorem of calculus that we can say that. The step right before it was because of the chain rule. So 2 powerful theorems were needed to prove this proof. Isn't that cool? And that concludes the proof. Exciting stuff. So now let's go back to that previous example. Which previous example? Well, the example where we did the line integral 3 separate times up here. This example 2, we did we used the same vector field and we did 3 different paths, and the only common denominator between those paths was, yeah, all 3 of them had the same beginning point of 0, 0 and the same ending point of 1, 1. But then we found that this vector field was conservative. And since it's a conservative vector field, we can apply the fundamental theorem of line integrals. We didn't even have to do any of that parameterization. We wasted a lot of time. Well, we didn't waste time. I mean, certainly you learned something from seeing examples where you had to do all the hard work. Since we know now that this line integral, we don't need to parameterize the curve. All we need is a starting and stopping point. And we got mama, we got fxy. Remember, it's a quarter x squared y plus c. Now, the c goes away when you evaluate your potential function between the starting and stopping points. So I'm not even going to use it. I'm just going to go, hey, this line integral, f dot with dr, is going to equal this function, fxy, evaluated between the beginning and ending points. So if I plug in the upper limit first, of 1, 1, and then minus, and then when you plug in the 0, 0, you're just going to get 0. This is just equal to 1/4, and we're done. Wasn't that the answer for all 3 of those line integrals for example 2? It was, and that's why they're all the same answer. because this vector field is conservative. Now, what about example 1 that we did earlier in the lecture? How come all 3 of those answers were different? On page 1, we had a similar situation where we did a line integral 3 separate times, but remember, we got 3 different answers. How come?
Is
Anybody
it
want-
because they weren't conservative?
Good. This vector field is not conservative. Well, what is the vector field? It's in here. You have to kind of cherry pick it off. The M is always going to be the stuff that's multiplying with the dx. And the N is the stuff multiplying with the dy. So there's M and there's N. So what it does, dm dy equal dn dx for this vector field? Let's check it. Well, let's see, dm dy looks like it's x, okay. And dn dx looks like it's 2x. They're not the same. So this is not a conservative vector field. And that's why it had 3 different answers every time we did the line integral, even though they had the same starting and stopping points for all 3 different situations. It's not conservative. So when you're trying to do a line integral with a non-conservative vector field, you will have to parameterize. Sorry. You will not be allowed to use the fundamental theorem of line integrals because that only works for conservative vector fields. And that's why our physics brethren, when they said this physics fact right here, why does it work? Because gravitational fields are conservative vector fields. Gravitational fields are conservative vector fields. And that's why you only care about the beginning point and the ending point when you're calculating the work done by a gravitational field on some object as it moves between the 2 points. Pretty cool, huh? That's a physics fact right there, folks. Congratulations. Okay, so let's do another example where we'll get to use this fundamental theorem. Okay, oh wait, we haven't finished this yet, sorry. You can extend it to space, but I haven't told you, so this theorem, I haven't told you how to prove a 3D vector field is conservative yet. So that one's going to be a little dangerous for you. Now, today's topic where you're we're looking at the fundamental theorem of line integrals. So this, you can do it for a 3D vector field, but first you have to show it's conservative. But it still will work. Once you get the mama, which will be a function of 3 variables, you certainly can evaluate between the starting and stopping points. And you'll get f evaluated at the ending point minus f evaluated at the starting point. And it'll work. Yay. So that's nice. Okay, now let's do an example. Example 3, it's not very hard. It's relatively easy. Let's evaluate this line integral. If the force field is this guy here and the curve is a smooth curve from the starting point to the ending point. Okay, now, right after I get done with this problem, I'm going to give you one to do. So I'm going to put you in breakout groups and try it. Okay, it's not in your course reader though, so I'll write it down. But I want you guys to try one. Now, folks, if this vector field weren't conservative, because they didn't give us how they went from the starting to the ending point, we wouldn't be able to actually evaluate the line integral because they didn't tell us if the path between these 2 points was a straight line or a curve or anything. And so when you have a non-conservative vector field, you have to have all the information at your fingertips of what the curve is doing in order for you to parameterize it and find the answer. But this one's conservative, so we don't care. We don't care how it got from the point -1,4 to the point 1,2. We really don't care as long as it got there. because of the fundamental theorem. Because check this out. Here's M and here's N. First, let's make sure that this is a conservative vector field by doing the test. dm dy has to equal dn dx. Okay, let's prove it. What is dm dy? Looks like it's 2x. Is that the same as dn dx? It's 2x. Yes, they're the same. So this is a conservative vector field. Like, okay, cool. What does that mean? Go get mama. That means there is a mama, a potential function. Let's go get it. Okay, m dx and n dy. All right, here we go. I need to integrate the first component, 2xy, with respect to x. That's not too hard. I get x squared y plus some extra junk. And I want you to say what that extra junk is. I'm going to use a different letter, by the way. How about if I use g of y instead of h of y? H of y is fine. And now the n dy, I need to integrate the other component here, x squared minus y, with respect to y. Okay, I'm going to get the first term is x squared y. Looks like I'm having duplicates. Minus y squared over 2 plus extra junk. Now, you're not allowed to use the letter g again. You already used it up when you did the g of y here. So if I see you, attempting to follow my rules, but then you use yucky notation, that's when I start docking you points. So pick something other than g. Like, how about h? We haven't used h yet. Fine. H of x. Since we were integrating with respect to y, we need to acknowledge that we are going to have some function here of x, the variable we didn't integrate with respect to. Now what? Put it all together. So don't add the duplicates together. Never do that. So I'm noticing both of those integration results have an x squared y. Please don't add them together. Don't go, oh, I got 2 of those. No. Just take one instance of it. But then we also have the minus y squared over 2. And there's always now going to be a plus c. So now what? This line integral f dot dr is going to be equal to x squared y minus y squared over 2. And you don't have to put the plus c when you're evaluating between the points. Well, why not? Because it'll cancel. You can go even try if you want. You'll have the plus c and then you'll have the minus. And then it goes bye-bye. So plug in the ending point first, which is 1, 2. So this is going to equal 1 squared times 2 minus 2 squared over 2. Minus, and then substitute in the beginning point. Negative 1 squared times 4 minus 4 squared over 2. Okay, and then do the arithmetic here. It's not my strong suit. What do we got here? Okay, clean up that mess. This looks like it reduces to 2, so 2 minus 2 is 0. That goes away, fine. 16 divided by 2 is 8, so 4 minus 8, negative 4, negative 4. Looks like a positive 4. Final answer, positive 4. And we're done. I applied the fundamental theorem of line integrals. Pretty exciting, isn't it? I want you to notice I didn't have to parameterize here at all. At all. And that's the beauty of it. So you guys ready to try one?
Yeah, let's do it.
Of course, yes. That's the attitude I like to hear. Thanks, Aaron. Okay, so you and a buddy are going to do this one. I got it all cooked up for you. Okay? And I'm even going to give you some weird notation at the same time. You're going to do this line integral. It's a differential form. Ooh, what? Yeah, you can. 2x over y dx minus x squared over y squared dy. So this is differential form. And so when you do this, and I'm going to give you some tips for approaching this one, I want you to do, I'm going to put some steps here that I want you and your buddy to do, okay? So the notation that's weird that I don't even think your book has, because it's not my favorite Calc 3 text. But what they'll do is they'll actually put the beginning point on the bottom of the integral symbol, and they'll put the ending point at the top of the integral symbol. Ooh, that looks kind of weird. I know, but that is a standard notation. So step one, I want you to prove the vector field is conservative. So please do that when you start with your buddy. So in other words, I want you to show me that dm dy is equal to dn dx. Well, how come? Because that proves to me that you're allowed to even use the fundamental theorem of line integrals. Otherwise, you're not even allowed to use it. Well, who's the m and who's the n? Remember what I told you, the m is always the junk that's multiplying with dx, and the n is what's multiplying with the dy. Now be careful, they're trying to trick you here with this minus sign. Do you think that minus sign is part of your n? It is. Because of the traditional differential form is understood to automatically by default have a plus sign. When they try to fool you with the minus sign there, and I do this to my differential equation students too, try to mess them up, because there is something to do with, it's called exact equations. So what I would do if I were you is change this minus sign into plus and negative, and then you'll have your n, okay? So prove it's conservative, and then step two, go get the potential function. That's go get mama. And then step three, apply the fundamental theorem of line integrals in that order, okay? If you stick to this procedure, it'll hopefully keep you on the right path, no pun intended, okay? So there it is. Y'all have that down? It's not in your course reader, so write it all down. Cornelius. Okay, so if we're doing step one, you got to prove the vector field is conservative here. You rewrite your m. You find dm dy. You rewrite your n. You find dn dx. And you see, oh, they're the same. The vector field is conservative. Yay! And now apply step two. Go get the potential function. Go get mama. So remember, to get mama, you have to integrate twice. And you're going to integrate the m with respect to x. And you'll integrate the n with respect to y. And then you'll sort of add the results, but you have to be careful because if you have duplicates, just take one instance of the duplicate, okay? So here I'm going to integrate 2x over y dx, okay? And I get x squared over y plus some function of x, or excuse me, of y, because I just integrated with respect to x, h of y. Then when I integrate the n, which we agreed was negative x squared over y squared, and you're going to integrate that with respect to y. What I would do is I would rewrite the y squared, bring it up to the numerator as y to the negative 2. And that way you can apply the power rule when you're integrating with respect to y. The negative x squared is a constant multiple. And then the antiderivative of y to the negative 2 is y to the negative 2 plus 1, which is negative 1. Divide out by negative 1 plus, you know, some function of x. And then clean this up and rewrite it with positive exponents only. And here we have a negative times a negative, so we'll have positive. And then we have our d of x. Now notice both these integrations gave us x squared over y. So we have duplicates. But what did I tell you about duplicates? Do not add them. Do not add together. That would be bad. Instead, your mama function, fxy, is take one instance of the duplicate and then plus c. So we just did step 2, congratulations, and now step 3, we're ready to go. What's step 3? We apply the fundamental theorem of line integrals. So what does that tell us? That tells us that this line integral that was given to us, and I gave it to you in an interesting format. You'll see this format more often in the homeworks that I put for you. This is simply going to be your function, your mama function evaluated between the starting and stopping points. Okay, so since mama really is only x squared over y, you're going to have 3 squared over 2 minus, and then when you evaluate at the lower limit, which is the beginning point, what do you get? You have 9 halves minus 9 halves minus 1. Is that right?
Yeah, 1.
But that's 9 halves minus 2 halves. And you should have gotten 7 halves. Yay! Everybody okay with this?
Yes.
Okay, fantastic. Then let's do a little bit of independence of path. I do want to at least get us to the point. I want to show you what a 3D vector field looks like when it's conservative, because it's kind of weird. It's not as easy as the 2D. Okay, but first let's do the independence of path. We're way back here. I skipped some stuff. Here we go. So the prep work is the following. From the fundamental theorem of line integrals, what we got is if f is continuous and conservative, both on an open region R, then the value of this line integral will be the same for every piecewise smooth curve from one fixed point to another fixed point. It won't matter what the path is. So we say that the line integral is independent of path, since it only cares what the beginning and ending points are. It's kind of like, I don't know if you guys have ever been on a plane trip. You know, like, yeah, let's say you're going to go fly to New York. Well, you could go on a nonstop if you're lucky enough to get one. Or you could go on a trip where you have a stopover or layover, maybe even 2 layovers. Like maybe they take you to Chicago and then you have to wait for 5 hours, and then you have to go from Chicago to, you know, somewhere else, and then finally end up in New York. But the fundamental theorem of line integrals would be, oh, I don't care about those layovers. Who cares? As long as you get to your destination, basically. So let's do a couple of weird definitions to prepare us to do the next theorem. So you have to know what it means to be connected. What is it? And this diagram over here pretty much shows you. It's a good picture. But mathematicians don't let diagrams be their definitions or proofs. They actually have to say it in words. So how do we say what this diagram says in words? And if you'll notice that the first region is connected. Well, how come? Because you can make it from the starting point to the ending point and stay in the region without ever leaving the island. On the other hand, this region that's got like 2 separate islands to it, you know, kind of like Hawaii has several different islands, even though it's considered one state. You can't get from point A to point B without leaving the region. You know, you end up having to swim in the ocean. So they say that that region is not connected. Okay. So in words, a region is connected if any 2 points in the region can be joined by a piecewise smooth curved line in the region. Fine. Now that you know what connectedness is, we can do this theorem. So here's what it says. It says if the vector field F is continuous on an open, connected, there's that new word, connected region, then the line integral, and we'll just do this generic line integral with a C f dot dr, is independent of path. IFF, what does IFF mean in mathematics? Anybody know what that's short for?
If and only if.
Good, if and only if. And the reason why IFF is different from a regular if is because it's what we call a double header arrow. You can read the sentence forwards and backwards and it'll still be true. Unlike a regular if statement, you have to read it only in the forwards direction for it to be true. So this one's cool because it's a double header. Double-headed arrow. You can read it forwards and backwards and it's still true. In fact, I'll read it forwards and backwards. I'll read it forwards first. We say this line integral FDR is independent of path if the vector field is conservative. Now I'm going to read it backwards and it's still true. If the vector field is conservative, then this line integral is independent of path. So I can read it both ways. It's still good. Let's do an example. So here's a vector field they're giving to us, 2x plus y cubed, 3xy squared plus 4. Prove that this line integral is independent of path. How would you do that? How would you prove a line integral is independent of path? I'm giving you a big hint right here. All you would need to do is show that what is true.
F is conservative.
Very good, very good. Exactly right. That is the trick. If somebody says, go prove that a line integral is independent of path, you tell them, sure, no problem. I can do that for you. I'll just show you the vector field's a conservative vector field. Okay, let's go do it. Yeah. And then they want us to evaluate this one right after we show that it is independent path. So all you have to do is simply show that F is conservative. And you're done. Well, is it? Well, here's M. Here's N. Does dm dy equal dn dx? Because if true, it's conservative. So let's go figure it out. Dm dy, that looks like it's 3y squared. Dn dx looks like, oh my, that's 3y squared also. They're the same. So therefore, conservative vector field. And by the theorem, therefore, by the theorem that we just learned, the line integral is independent of path. What does that mean, independent of path? It means you don't care how it gets from the start point to the ending point, as long as you get from the start point to the end point. You know, like here's your start point, here's your end point. You could do a straight shot, or, you know, like a nonstop flight, or maybe you go over here first and then down here and then around and woo, you know, all over the place. And then you finally make it to your destination. Yeah, it doesn't matter how you get there. It's independent of path as long as you get there. All right. So we just proved independent of path. Now let's actually evaluate that line integral. Okay. Well, I'm going to use the fundamental theorem of line integrals because I can. Because I don't have, they didn't give me enough information to parameterize. They didn't tell me how I got from the starting point of 0, 1 to the ending point of 2, 3. So I wouldn't even have enough to parameterize anyway. So the fundamental theorem of line integrals is valid for this problem because it's a conservative vector field. So we're going to use it. We're going to use. So what does that mean? Go get mama. Yeah, we got some work to do. Yeah, we got to go get mama. Otherwise, we won't be able to evaluate. Yeah. So let's go do that. So we're going to have to integrate the m with respect to x. So the m is the first component, and that's 2x plus y cubed. And when we integrate that with respect to x, I get x squared plus xy cubed plus extra jump, h of y. Then integrate the n with respect to y. So for us, they gave us that second component for this vector field, 3xy squared plus 4. Integrate that with respect to y. Okay. Xy cubed plus 4y plus g of x. Okay, then what? Your potential function, that's mama, is going to be, pretty big, x squared plus, now you have duplicates here. Do not add these together. No. Just take one instance of it, xy cubed, plus we got a 4y. Aha, got a lot of stuff going on here. Is that the case all the time? Sometimes you might get a large potential function. So then what? Well, this line integral that they want us to do which has a beginning point of 0, 1 and an ending point of 2, 3, is simply going to be the mama function evaluated between 0, 1 and 2, 3. Yeah, it's that easy. So always do the ending point first. So you got 2 squared plus 2 times 3 cubed plus 4 times y minus, and then substitute the beginning point, 0 squared plus 0 plus 4 times 1. You know, what do you get here? 2 times 27 plus 12, and then distribute your negative minus 4, and then do the arithmetic, and I get 66. And we did it. We proved that it was independent of path, and we got the answer. Worked out pretty well, right? I know, Esteban, yeah. So that concludes that example. Now, what about this other example here? Like, how would you prove that this line integral given here is not independent of path? How do you think you would do that? It's very easy. It's exactly what you think. Prove that f is not conservative, and then you'll have shown that it is not independent of path. Okay, so the m is the x squared y. So what is dm dy equal to? Well, the derivative of x squared y with respect to y is x squared. And then the n is 3xy squared. So dn dx is 3y squared. And these are not the same. You know, we can say, hey, dm dy is not equal to dn dx. So not conservative. And therefore, by the theorem, not independent of path. So what does it mean not to be independent of path? It means you care about the path, like you care very deeply about the path. In other words, you want to know exactly how they got from the starting point to the ending point. Was it a straight line? Was it a curve? What was it? And they didn't give us enough info here. They just gave us a start and stop point. They didn't tell us if it was on a curve or a straight line. And so we don't even have enough info to evaluate the integral. The answer is no, 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 no. Not enough info to evaluate that line integral. Sorry. Too bad. Because you would need to parameterize. You need some information about that path. Because you're going to have to, if you were to evaluate the line integral, you have to do that whole brute force, parameterize, and so on. Now, I do want to show you how a 3D vector field is conservative, because I've been holding back. I kind of do it a little differently from the textbook. The textbook gives you how to do a 2D proof that a two-dimensional vector field is conservative at the same time as a 3D, but I like to hold off. But now you're ready. Good news and bad news. The good news is there's a little piece of this that's the same for a two-dimensional vector field. So one thing you're going to have to show when you have a 3D vector field where the components are labeled M, N, and P in that order, it's conservative if and only if. You still have to show that dm dy is equal to dn dx. So this is the same as the 2D. But you have to show two other things are true at the same time. You have to show that dp dy gives you the same result as dn dz, and dm dz has to equal dp dx. All three of these have to be true simultaneously. If even one of them isn't true, but the others are, it's not a conservative vector field. Sorry. All three have to be true. Okay. And then further, there's this thing known as differential form, and then an exact differential form. So what does it mean to have a differential form be exact? It's exact if and only if the vector field is conservative. So if you have a 3D vector field, then that would mean you would need all three of these things to be true. You need dp dy to equal dm dz, and dm dz has to be the same as dp dx, and you need dn dx to be equal to dm dy. If all three of those are good, you got a conservative vector field, and you have what's known as exact differential form. Now, for those of you who are taking differential equations, or you're going to next semester, you will learn a type of differential equation called an exact differential equation. And to prove some of DE, a differential equation, is exact, you're basically showing that the vector field involved is conservative. So you learned it here first. Congrats. So I wanted to do one of these and then I'll let you go, okay? And we'll finish this up next time because it's Friday. So here is a 3D vector field. Oh my goodness. Prove that this line integral is independent of path and then evaluate this line integral. Well, how do we prove it's independent of path? Show it's conservative. Yeah. So we have the M and the N and the P. So, and we know what the test is now for a 3D vector field to be conservative, right up here. Right there. You need all three of those things to be true simultaneously. I don't even try to memorize them. I always look it up. Too hard to memorize everything. Okay. So what is dn dx? I get 2y cos x. Is that equivalent to dm dy? Well, look at it. Here's m. What is the derivative of that with respect to y? I claim it is 2y cosine x. So yes, those guys are equivalent, okay? What else? We need dp dx, whatever that's equal to. Is that going to be the same as dm dz? Let's check it out. dp dx. P is the last component. So if you look at the p, you'll notice it's 2y e to the 2z power. There is no x. So what's the partial of that with respect to x? 0. Well, is that the same as dm dz? If you look at m, you'll notice it doesn't even have any z's in there in that expression. So dm dz is equal to 0. Aha, so dp dx is the same as dm dz. Cool, we're 2/3 of the way there. Now, one more check. Is dp dy going to give us the same answer as dn dz? Okay, dp dy is 2e to the 2z. Is that the same as dn dz? And I claim it is. So since all three of these are satisfied, the vector field is indeed conservative. And what does that mean? By the theorem, the line integral is independent of path. So by the theorem that we just studied, the line integral is independent of path. Now what? Go evaluate the line integral. We got to go get mama. So how do you get mama for a 3D vector field? And that's why I wanted to kind of finish with this. You're going to have to do 3 integrals. I know. You got to get mama. So let's get that potential function for this conservative vector field. So you're going to have to do m dx, you're going to have to do n dy, and you're going to have to integrate p dz, and then add the results. Of course, if there are any duplicates, don't add the duplicates together. Okay, please. Just take one instance. So the m for this vector field was y squared cosine x. And when we integrate y squared cosine x, with respect to x, it's y squared sine x. All righty. Plus, now here's the weird part. This is a little bit different than a 2D vector field. We're integrating with respect to x, so there are 2 other variables that we didn't acknowledge in this one integration. So when you have a function, call it h, you have to acknowledge the other 2 variables that we didn't integrate with respect to. And it could include a constant, h, y, comma, z. Put that in there, otherwise prepare to die. All right, now we're going to do the second integration. We're going to integrate the n, which is 2y sine x plus e to the 2z power. And that needs to get integrated with respect to y. Okay. First term, I get a y squared sine x. The second term, I'm going to get y e to the 2z plus, I'll call it, g of y z, or excuse me, g of, how about the other 2 guys that we had there, g of xc. Mhm. Do you notice I do have duplicates already starting here? Just to see, you got the y squared sine x showing up in both of those results. So be careful because you don't want to add those together. So now we're going to wrap it up here with the PDZ. So that last component of the vector field was 2y e to the 2z. And we're going to integrate with respect to z. And if you use the exponential rule here with some u sub, you're going to get that you need a 2, but you already have a 2. So you really have y e to the u du here, which is y e to the u, which is y e to the 2z, plus some extra junk. I don't know, you're going to use up a different letter here. I don't know, call it t of xy. And then finally, we have the potential function, which is a function of 3 variables, x, y, and z. You take one of the duplicates, y squared sine x, and then you've got that other guy, the y e to the 2z. And notice that that showed up twice also. Don't add them together, plus c. So now what? Finally, this line integral that they want us to evaluate, f dot dr, is going to be the potential function evaluated between the starting and stopping points. So you just do a lot of substituting here. So you're going to go 1 squared sine pi halves plus 1 e to the 2 times 1 minus negative 1 squared sine 0 plus negative 1 e to the 0 power. Sine of pi halves is nice, it's 1, but sine of 0 is 0. So this is going to end up being kind of a weird answer. It's 1 plus e squared, then minus minus a 1 is plus 1. So we get 2 plus e squared is the final answer. That's the exact answer. Okay, pretty weird, but that is the result of the line integral. Okay, and we're done with that example. And that'll conclude today's lecture. Congratulations. You now know the fundamental theorem of line integrals. Yay!